Welcome to this lesson on real numbers and their properties. We'll cover decimal expansions, rational and irrational numbers, absolute value, and the key properties of real numbers: closure, associative, identity, inverse, commutative, and distributive. Every idea comes with a step-by-step worked example, so let's get started. By the end of this lesson, you'll be able to do 6 things: classify decimals as terminating, non-terminating recurring, or non-terminating non-recurring. Tell the difference between rational and irrational numbers. Recognize the real numbers as the union of rationals and irrationals. Find the absolute value of a real number. Demonstrate the closure, associative, identity, inverse, and commutative properties, and verify the distributive property over addition and subtraction. Every decimal number falls into one of 3 categories. A terminating decimal is one where the division simply ends, like 3 divided by 8, which equals 0.375. A non-terminating recurring decimal never ends, but a digit or block of digits repeats forever, like 1 divided by 3, which equals 0.333 repeating. And a non-terminating, non-recurring decimal never ends and never settles into a repeating pattern, like the square root of 2. That last type is what we call irrational, and we'll get to that shortly. A rational number p over q gives a terminating decimal when, in its lowest form, the denominator has only 2's and 5's as its prime factors. Let's apply that rule. 8 equals 2 cubed, so 3 over 8 must terminate. Watch the long division. Since 3 is less than 8, we write 3 as 3.000.30 divided by 8 is 3, remainder 6, giving us 0.3 so far. 60 divided by 8 is 7, remainder 4, giving us 0.37, and 40 divided by 8 is 5, with remainder 0, so we stop. The answer is 3 over 8 equals 0.375. Sometimes a decimal never ends, but one digit or a block of digits repeats forever. We show that repeating part in brackets. For example, 1 over 3 is 0.3 repeating, which we write as 0.3. Let's convert 0.6 repeating back into a fraction. Let x equal 0.666 and so on. Multiply both sides by 10, giving 10x equals 6.666. Now subtract the original equation from this one. 10x minus x equals 6.666. Now subtract 66 minus 0.666, which leaves us with 9x equals 6. Divide both sides by 9 and x equals 6 over 9, which simplifies to 2/3. So 0.6 repeating equals 2/3, and every recurring decimal is, in fact, a rational number. Now for the third type. These decimals go on forever with no repeating pattern at all, which means they cannot be written as a fraction. They're irrational numbers. Classic examples include the square root of 2, which is approximately 1.41421356, the square root of 3, pi approximately 3.14159, and Euler's number e approximately 2.71828. Keep in mind, these written decimals are only rounded approximations. The true values never end and never repeat. A rational number is any number that can be written in the form p over q, where p and q are integers and q is not 0. This includes integers, fractions, terminating decimals, and non-terminating recurring decimals. For example, 1 over 2, negative 3 over 4, and 7 over 1. Every integer like 5, negative 8, or 0, 0.75, which terminates, and 0.333 repeating. Rational numbers actually contain smaller nested sets inside them. Natural numbers sit inside whole numbers, which sit inside integers, which sit inside the rationals. An irrational number is one that cannot be written as p over q. Its decimal expansion is non-terminating and non-recurring. Common examples include the square root of 2, 3, 5, and 7, roots of numbers that aren't perfect squares, along with pi and Euler's number. Here's a quick idea of why the square root of 2 is irrational. Suppose it were rational, equal to p over q in lowest terms. Squaring both sides gives us 2 equals p squared over q squared, so p squared equals 2q squared, which means p squared is even, so p itself must be even. If p equals 2k, then substituting back shows q must be even too. But if both p and q are even, they share a common factor of 2, which contradicts our assumption that the fraction was in lowest terms. So the square root of 2 cannot be rational. Let's compare them side by side. In terms of form, rational numbers can be written as p over q, while irrational numbers cannot. Rational decimal expansions terminate or repeat. Irrational ones never terminate and never repeat. Rational examples include 1/2, -3, 0.75, and 0.333 repeating. Irrational examples include the square root of 2, the square root of 3, pi, and e. On the number line, rational numbers densely fill the gaps between integers, while irrational numbers fill in the remaining gaps. Put the two sets together and you get the real numbers. The real numbers, R, are the union of the rational numbers, Q, and the irrational numbers, Q prime. These two sets are disjoint. They share nothing in common, but together they make up every single real number there is. The absolute value of a real number x written between two vertical bars is its distance from 0 on the number line, and distance is never negative. If x is greater than or equal to 0, the absolute value is just x. If x is less than 0, the absolute value is negative x, which flips it positive. For example, the absolute value of -3 is 3, and the absolute value of +3 is also 3. Both are exactly 3 steps from 0. Let's evaluate an expression. The absolute value of -9 plus the absolute value of 4 minus the absolute value of -2. That becomes 9 plus 4 minus 2. 9 plus 4 is 13, and 13 minus 2 is 11, so the final answer is 11. Real numbers follow 5 key properties under both addition and multiplication: closure, associative, identity, inverse, and commutative. Closure means a plus b or a times b always stays inside the real numbers. Associative means grouping doesn't matter. Identity means adding 0 or multiplying by 1 leaves a number unchanged. Inverse means every number has an opposite that undoes it. And commutative means order doesn't matter. Let's look at each one in detail with worked examples. The closure property says that for any two real numbers, a and b, both their sum and their product are always real numbers too. The result never leaves the set. For example, 2 plus 3 equals 5, and 5 is a real number. 2 times 3 equals 6, also a real number. Even mixing in an irrational number works. The square root of 2 plus 3 is approximately 4.4142, still a real number. Here's an interesting exception, though. Irrational numbers alone are not closed under addition or multiplication. The square root of 2 plus negative square root of 2 equals 0, which is rational, not irrational. And the square root of 2 times itself equals 2, also rational. So closure strictly holds for the real numbers as a whole, but not for the irrationals by themselves. The associative property tells us that when we add or multiply 3 or more numbers, how we group them doesn't change the result. For addition, 2 plus 3, in parentheses, plus 4 equals 5 plus 4, which is 9. And 2 plus, in parentheses, 3 plus 4 equals 2 plus 7, which is also 9. For multiplication, 2 times 3 times 4 equals 6 times 4, which is 24, and 2 times, in parentheses, 3 times 4 equals 2 times 12, also 24. Either way you group them, the answer stays the same. 0 is the additive identity. Adding 0 to any number leaves it unchanged, like -7 plus 0 equals -7. 1 is the multiplicative identity. Multiplying by 1 leaves a number unchanged, like 9 times 1 equals 9. Now for inverses. Every real number a has an additive inverse, -a, so that a plus -a equals 0. For example, the inverse of 5 is -5, since 5 plus -5 equals 0. And every non-zero real number a has a multiplicative inverse, 1 over a, so that a times 1 over a equals 1. The inverse of 4 is 1 over 4, since 4 times 1 over 4 equals 1. Note that 0 has no multiplicative inverse. The commutative property says the order of the numbers being added or multiplied doesn't change the result. For addition, 3 plus 7 equals 10, and 7 plus 3 also equals 10. For multiplication, 3 times 7 equals 21, and 7 times 3 also equals 21. But this property does not hold for subtraction or division. 5 minus 3 is 2, but 3 minus 5 is -2. Those are not equal. And 10 divided by 2 is 5, but 2 divided by 10 is 0.2, also not equal. So the commutative property applies only to addition and multiplication. The distributive property connects multiplication with addition and subtraction. A times, in parentheses, b plus c equals a times b plus a times c, and the same works for subtraction. Let's verify it. First, over addition, 4 times. In parentheses, 5 plus 3 equals 4 times 8, which is 32, and 4 times 5 plus 4 times 3 equals 20 plus 12, which is also 32. Both sides match, verified. Now over subtraction, 6 times. In parentheses, 9 minus 4 equals 6 times 5, which is 30, and 6 times 9 minus 6 times 4 equals 54 minus 24, which is also 30. Both sides match again, verified. To wrap things up, let's review the key takeaways from today's lesson. First, decimal expansions can be terminating, non-terminating recurring, both of which are rational, or non-terminating non-recurring, which are irrational. Second, rational numbers can be written as p over q, while irrationals cannot, and real numbers are the union of these two disjoint sets. Third, the absolute value of a number represents its distance from 0 and is always non-negative. Fourth, the set of real numbers is closed, associative, and commutative under addition and multiplication, with clear identity and inverse elements. And finally, the distributive property successfully links multiplication over addition and subtraction